over the equations of motion. Thanks for starting that recording. Yeah, so today we're going over the equations of motion, and let me go ahead and switch over to my OneNote. All right. Okay, so hope everybody can hear me fine. Hope everybody had a good night and enjoyed their camps yesterday. So today's the last day. And today we'll be going over the equations of motion, also known as kinematics. So, just kind of like how we started yesterday, I kind of want to start with some definitions, and then we can kind of dive into more of the math and physics of what we're going to talk about today. So, I have a basic kind of definition here for kinematics, and basically kinematics deals with how objects move, and it differs from dynamics, where dynamics deals with forces and why objects move the way they do. But both of these are, considered mechanics. And then, mechanics basically breaks down into kinematics and dynamics. So, in order to basically talk about kinematics, we have to define, these three things here: displacement, velocity, and acceleration. So that's pretty much where we're going to start at. So displacement and distance, which you're probably already familiar with displacement and distance, but just to remind you how they differ is if we were, say here at this location, let's say this is Walmart. It's called WM for Walmart. And let's say over here is Target, right? So if you're at Walmart, you want to drive to Target, you pull out your GPS and you basically GPS from Walmart to Target. And the GPS may look something like this, you pull out of Walmart, let's say you go up here, go down that way, and you got to take some road that looks like this, stop there, go down this way, and then turn up into Target. So basically what I've just drawn here is the path that you would drive in your car to basically get to Target. And we kind of see this path has all kind of, left turns, right turns, curves, etc., etc. So if you were to measure out, how far that is, that would give you your distance. So this black line here basically represents the distance, uh, I guess, yeah, the distance from Walmart to Target, taking this path here. And how that differs from displacement is displacement basically measures from Walmart directly to Target in a straight path. So let's do it like this. So from there to there would be how your displacement is represented. And so we can see here basically your displacement is actually shorter than what the distance traveled is. And I also use that arrow here to represent displacement because displacement is indeed a vector, whereas distance is a scalar. Let's just scale, I think it's AR, scalar. All right, so that's pretty straightforward, your displacement, and I guess I'm going to use the letter S to represent displacement. Right, and then for distance, I guess I'll just represent that with the letter D. Okay, so that's pretty straightforward. And so Basically, after displacement, we kind of now have to understand velocity and speed, which is very similar to displacement and distance. We know velocity is going to be some vector. So I represent it with the V with the arrow on the top because we know velocity is a vector. And velocity is basically given by the displacement. And I guess I should write the displacement like this. It is delta S, where basically this is S final over here, and over here this is S initial. Some people like to use 1 and 2 or 0 and 1. I'll just be using this circle for initial and then this F for final. But in other places, you can also label it as, S1 and S2, or you can label it as S0 and S1. Either way, just kind of know that, which one's your final destination, which one is your initial destination. So your velocity, our velocity, and this is a vector, is going to be given by the change in the displacement, or just the displacement actually, final minus initial, divided by the change in time, where this change in time is basically just how long it takes to go from, let's say Walmart to Target. And so this is a vector quantity, this velocity, and how it differs from speed is speed, instead of displacement, is given by the distance. So the distance d, I just write distance, over the change in time. So velocity is the displacement over time, whereas the speed is the distance over the time. Okay. And then lastly, we have our acceleration, which, as you can probably guess, the acceleration is also a vector, and it is just the change in the velocity over the change in time. And so I could also write this as, V final minus V initial divided by, T final minus T initial. And similarly, I could have done that for the velocity. Written it out as velocity is S final minus S initial over T final minus T initial. Okay. So this is kind of the basis here of kinematics. So starting with displacement, we have a velocity and we have acceleration. Now, I'll also briefly mention that these are actually the average velocity and the average acceleration. So this is actually the average velocity, and this is actually the average acceleration. And just kind of real quickly, I'm skipping a bit, but I just want to kind of show how these differ from instantaneous velocity and instantaneous acceleration. So you can kind of imagine here, if this is a, let's say this is a position time graph, and let's say actually let's just call it X, somewhere on the X-axis. So this is a position time graph, and let's say your graph looks something like this. And so if say we choose 2 points on this graph to find the average velocity, let's say we choose this point here, where this is going to be our X final, and some point here, where this is our X initial. Using both of these points and the time, this is T initial, over here be T final, we can find basically the average velocity is average velocity here, which is basically the final position minus the initial position divided by the change in the time here. And so to give us basically a slope, it looks like this. So that line basically represents the average velocity here. Now, instead of the average velocity, let's say you wanted to find the, the velocity at a certain instant. Let's say at this point right here. Let's say you want to find the velocity at this singular point, which would be the instantaneous velocity. So what we would do is we would actually take this here, this delta S over delta T, and would basically take the limit, and let's say this is time, let's call it time T1. We can take the limit as the time T approaches T1, and this limit basically would give us the instantaneous velocity at this point, which would actually be the slope at that point right there. And so if we take the limit to at that time there, that basically gives us, we can actually write it this way. Now we can basically write it as a derivative, and that gives us our instantaneous velocity. So I just wanted to mention that there is a difference between average velocity and instantaneous velocity. So this slope here on here at this point giving us the instantaneous velocity, whereas the average velocity takes 2 points and gives us the slope of that line. Okay, so of course the next thing to do would be to kind of do some examples to kind of solidify, all this stuff we just talked about. So here I have a simple example I'm going to work through. It says a bird moves along the sky in the x direction. Its position as a function of time is given by the equation, I'll write that again here, x equals 3 times the time squared plus 1. So that's our equation for the position as a function of time. And it says find the displacement during this time interval here from 3 to 5 seconds, and then also find the average velocity for this time interval, and then as well as finding the instantaneous velocity at 5 seconds. Okay, so first let's find our displacement. Let's kind of draw a picture. Well, I guess you can kind of just visualize it. I guess this is our bird, and we know it's fine in this x direction here. So it's basically in one dimension because it's fine in the x direction. And that's also why instead of s, they're using x. So if we want to find a displacement, displacement is from 2 points. Let's say like right here, it's time 3, and then over here, it's time, this is what a time equals to 5. Seconds and seconds. So there's basically 2 points, a final position and an initial position. So basically the displacement is going to be the final position minus the initial position, right? And so the initial position is going to be x naught is when the time is equal to 3. So using this equation here for position as a function of time, we can just plug in 3. So we have 3 comma, this is 3 squared now, plus 1. And so the initial position at 3 seconds is going to be, see, 3 times 3 is 9, times 3, 27, 28 meters. And then we do that again for our final position. So our final position is when the time is equal to 5 seconds. So just plugging that in, 5 squared plus 1. Let's see, so 5 times 5 is 25. 25 times 3, 75, 76 then, plus 1, 76 meters. Okay, so now we have our initial position, 28, our final position of 76. And so the displacement in the x direction is simply going to be 76 minus 28, which gives us, let's see, 48. Meters. Okay, so not too bad. This is our displacement now. So let's see, the next part of the question says, now find the average velocity. Find the average velocity. Well, the equation we have here for our average velocity is the displacement divided by the change in time. So let's see, our average velocity then is going to be the displacement, which we found here, is 48 meters. Divided by the time interval, or t final and t initial, where t final was 5 and t initial was 3. So we have 5 minus 3, which is just 2. So 5 minus 3 is 2. 48 divided by 2 is, let's see, 24. So now these are going to be in meters per second. So this is our average velocity over this time interval here, 3 to 5 seconds. And then the last part of this question says find the instantaneous velocity at 5 seconds. So as I mentioned earlier, the instantaneous velocity is given by this derivative here. So basically we take the derivative of basically our position or our displacement with respect to time. So here we have this equation here in the x direction with respect to time. So our velocity, put it in a different color, our instantaneous velocity, you can write it this way as the derivative in the x direction with respect to time. So now we're just taking a time derivative. So this is kind of going back to calculus of 3t squared plus 1. And we also want to evaluate this derivative. So I'm going to draw a line and say at t equals 5. And so first let's take our derivative. And whenever we take a derivative, we take our exponent and bring it down to the front. So this exponent comes down, multiplies with that 3 to become 6t. And the derivative of just 1 is 0. And now we're evaluating this 6t when t is equal to 5. And And so we get that the instantaneous velocity at 5 seconds is basically 5 times 6 after we plug in 5 into the 6, 5 into the t, into the time. And let's see, get 30. Cool. So notice here that the instantaneous velocity at 5 seconds is different from the average velocity over the time interval from 3 to 5 seconds. And so one more example here to kind of solidify, you know, all of this info before we move on. So another example I have here is, says an automobile is moving to the right along a straight highway, which we choose to be the positive x-axis, and a driver puts on the brakes if the initial velocity is 15 meters per second and it takes 5 seconds to slow down to the final velocity of 5 meters per second. What is the car's average acceleration? So of course, I'm going to draw a picture here, because the first thing you always want to do is to draw a picture, even though you may not need it. The pictures kind of save you from making certain mistakes you might not have made, if you didn't draw a picture. So we know initially, well, the car is braking here, and let's see, let's draw skid marks, I guess. And so we know the final velocity over here is going to be, 5 meters per second. Our initial velocity, this starts right here, is going to be 15 meters per second. And let's see, that's basically, and the time it takes for to slow down from 15 to 5 is, I guess what we can really call this T naught over here. So it takes 5 seconds. So we can also say it just takes 5 seconds, or we can think about it like the initial time is 0 and the final time is 5. So it's be like time total. And so now to get our average acceleration here, we would just use this equation here for the average acceleration, which is the final velocity minus the initial velocity divided by the final time minus the initial time. So our average acceleration is going to be t final minus t initial. So we have 15, or 5 actually. 5 minus 15 divided by 5. And so this gives us, let's see, 2 gives us actually negative 2 meters per second squared. And so notice here that we actually get a negative number, which makes sense with the problem because this object is actually slowing down, and since we know acceleration is a vector, this negative just means the acceleration vector was pointing in this direction, in the negative direction. And so here, I guess it's good for me to point out how the velocity vector and acceleration vector kind of interact with each other. Oops. Okay. So for this problem, we had our velocity vector, and if I were to draw the velocity vector, it'd be pointing in this direction because we know it's going towards the right. And as this car here moves towards the right with this velocity, it, oh my gosh, sorry.
Um, your audio's off, Ashton. We can't hear you.
Oh man, I'm so sorry. I was muted. So let me go back a little bit. I think I was last talking about this velocity and its acceleration before I got muted. Basically, I was just saying that as we calculated the average acceleration here, we saw that the average acceleration ended up being negative, which just indicates that, the acceleration vector is pointing to the left, whereas this velocity vector was pointing towards the right. And when these acceleration and velocity vectors point in opposite directions, it just means that, this car here is slowing down, versus if the acceleration and velocity vectors are going in the same direction, it means the object is speeding up. So if this is our acceleration vector and our velocity vector pointing in the same direction, this means an object is speeding up. And if the velocity vector is in the opposite direction of the acceleration, then the object is slowing down. Cool. So next, I wanted to move on and just talk about a motion with a constant acceleration in one dimensions. And so by one dimension, we mean it's just along a singular axis, either going to the left and the right in the x-axis, or an object that's just going up and down in the y direction on the y-axis. So it's useful to kind of analyze a situation that has constant acceleration because we can often make good estimations by just assuming the acceleration is constant. And whenever you approach a word problem, they'll most likely say or give you the acceleration so you'll know whether if it's constant or not. There are cases where the acceleration may not be constant, and we just kind of handle those slightly differently. But first, let's analyze this constant acceleration. And the way I kind of want to analyze this is with some an acceleration time graph, a velocity time graph, and a position time graph. And so I'll also show you here the equations of motion that basically come along with assuming the acceleration is constant. So if you ever, approach a problem and they say the acceleration is constant, you can automatically think and jump to these equations here. And so with these graphs here, I kind of just want to show you where those equations come from. So first, looking at this acceleration time graph, if we assume that the acceleration is constant, on this graph here, how do you think, we would graph out a constant acceleration? And of course, just something to quickly think about. So the acceleration would be just a straight line, like so, right? Because the acceleration is constant. So for example, let's say the acceleration here, is constant, 5 meters per second squared. And so this would be an example of a constant acceleration. And of course, the acceleration doesn't have to be positive. It can also be negative. So it can also show up below the graph down here. And you could also have a negative constant acceleration. Okay. But really, what I want to analyze with you guys here is this velocity time graph. So if the acceleration is constant, then how would that affect our velocity time graph? Well, our velocity time graph would look like this. It would be a straight diagonal line. Kind of like so. Well, of course, it can also be a diagonal line going downwards, or it can actually be, any kind of which way, but it's going to be a line, basically a linear line that has, a constant slope. So let's kind of look at this graph here. If we were to analyze it and say, what is the slope of this line, from this point in, let's say this is V0, to this point here, if this is V final, we can find the slope of that, where we know the slope is given as the rise over the run. So the slope is given as the rise, which is going to be basically how high this goes up. So how high it goes up here. And so this height is basically V final minus V initial. Not to confuse it with the total kind of height here. But the height from the starting position to the final position is going to be V final minus V initial divided by the run, which is going to be the time, divided by the time. And so if we look at this here, we kind of notice that this is basically the same equation that gives us the acceleration. Because acceleration is basically the final velocity minus the initial velocity divided by the time. And so now we can rewrite this equation to give us one of our equations of motion. So if I kind of just manipulate this to solve for V final, and I see that V final is equal to multiplying the time over and adding over the initial velocity gives us this equation here. And this is one of the equations of motion that we can just kind of always use whenever the acceleration is constant. So if we look down here, that would correspond with this equation here. So now let's see how we get these other equations of motion with this graph. So now instead of analyzing the slope, let's look at the area underneath this curve. So if we look at the area underneath this curve, let's say we have this portion here on the bottom, which makes kind of a rectangle. And then we also have this portion here that makes this right triangle. So altogether, this would be the total area underneath the curve. And so for a velocity time graph, the area underneath the curve should actually give us the displacement. So let's see, let's solve for the area underneath that curve there. So if we start with this little rectangle down here, the area of that rectangle would just be the initial velocity, this height, which would be the initial velocity, times the time, right? So we have the initial velocity times the time. Then also we have the area of this triangle here. The area of the triangle is 1/2 base, the base which is time t, times height, where the height is going to be v final. So this height here, from there to there, blue. The height from here to here is v final minus v initial. Alright, and let's see, so we can actually substitute this part here, this v final minus v initial. We could substitute it for here. We see v final minus v initial, and if we multiply the time over, we see that v final minus v initial, right here, v final minus v initial is actually equal to the acceleration times the time. And so if we take that, we can plug that in and replace this v final minus v initial, and we end up with a times t squared. And again, I said before that the area underneath the curve basically gives us the displacement. So this displacement S is the area underneath the curve, and the area underneath the curve ended up giving us this equation here. And so now if we scroll down to show you the equations of motion, that would correspond with this first equation. And so now we have basically the first and second equations of motion, and we're able to basically find those just from looking at the velocity time graph. And so these other two equations, well, actually this third one, you can actually find from combining equation 1 and 2, which I'm not going to go through, but if you wanted to go through the algebra, you would take equation, I remember these 1 and 2, and they would give you this equation here, this third equation. So you basically take equation 2, solve for the time, and then plug that into equation 1 to give you an equation here that is basically independent of time, because there's no variable for time in there. And this last equation here, again, we can also actually find this from the velocity time graph here. Because another way we can find this area underneath the curve, we see that this total area makes a trapezoid. Kind of like so, right? And so there's also an equation for the area of a trapezoid, and that would basically be, so I'll write it right here. The area for a trapezoid is, let's see if I remember correctly, it should be the base. Well, it's actually going to be, I guess, one side plus the other side, right? So we have V naught, which is this side here, plus V final, which is this bottom or right side here, plus V final, divided by 2 times the, if you were to like shift this way, this is kind of how I'm thinking about it. And so time would basically be the height, so times the height t, and that's basically just the area of a trapezoid. It's going to be, this top length plus this bottom length divided by 2 times the height t here. And so now we see this gives us the last of our equations of motion here. So it corresponds to equation 4. Alright, cool. So I just think it's kind of good to see, where these equations of motion kind of come from. That way, you don't just have to memorize them. Even though in most cases you'll probably have a formula sheet with these written down, but it's still kind of helpful to see where, those equations kind of come from. Let's see. So I guess the last thing I'll mention about this is how the acceleration time graph, velocity time graph, and position time graph kind of all relate to each other. So we've kind of already analyzed the velocity time graph pretty well. We know that for a velocity time graph, velocity versus time. And whenever you analyze a graph, it's real important that you note what's on the axes, because it's kind of easy to miss that and it can kind of mess up your thought process. So for a velocity time graph, if you take the slope of it, if you take the slope of a velocity time graph, it gives us the acceleration. And if we find the area underneath this curve for a velocity time graph, it actually gives us the displacement. And so what's interesting about that is, because we know we can write the velocity this way. Velocity is dx dt. And we can also say acceleration is dv dt. And then finally, actually, yeah, that's it. And so similarly, if we look at the acceleration versus time graph, so this is our acceleration versus time. If you look at this graph, the area underneath this graph, so this area here, actually gives us the velocity. similar to how the area underneath the velocity time graph gives us the displacement. Okay, and then lastly, I'll kind of draw out how the graph looks for a position time graph. So the position time graph actually looks like a parabola, like so, which makes sense because if you look at basically this equation here for displacement or position versus time, it has a time squared here, and so we know it's going to make some type of parabola shape. Hence the, this is our position time. This is position versus time graph. Okay, so all that was just kind of to show and explain how we get these 4 equations of motion here. So now that we have these equations of motion, let's go ahead and apply them to some problems to kind of see how they work. So this first problem here says an airplane must reach a velocity of 30 meters per second before it can take off. If the plane starts off at rest and can accelerate at 2 meters per second squared, if the runway is 150 meters long, then can the plane reach the proper velocity to take off? If not, what is the minimum length the runway must have? So traditionally, how a professor would teach this is they would say, write down all your knowns and write down your unknowns. So just for the sake of kind of showing you what you'll kind of see in class, I'm going to go about it that way. So we have our knowns and our unknowns. So we have our knowns and unknowns. So it's good to kind of label the things that we know. So we know that the acceleration here is 2 meters per second, and that indicates that the acceleration is constant. So once you see basically this part here, that the acceleration is a definite number, like 2 meters per second, then we can automatically assume, well, we must need these equations here. So we know the acceleration is 2 meters per second squared. Let's see what else we know. We also know the displacement is going to be 150 because it's actually just a straight line. It's just a runway. So let's actually draw a quick picture. So this would basically be our runway. We could say right here is x naught, which would be 0. Over here would be x final, which would be 150 meters. And the plane basically starts off over here. Our plane starts off over here, and by the time it gets 150 meters, or to this point here, it must have a velocity of 30 meters per second. So let me write out the displacement. So I'll write it this way. No, the displacement S is x final minus x initial is 150 meters. And so this first question asks us, can this plane, reach the proper velocity to take off. And so basically we want to know if the final velocity over here is going to be at least 30 meters per second, so this plane could take off. And I think I missed this part here. It also says the plane starts off at rest. It's also key to indicate because that tells us the initial velocity is 0. Okay, and so the unknown here is going to be v final. All right, so we know the acceleration, know displacement, and we actually know the initial velocity based off of this question here. And we want to find what v final is after this plane accelerates 150 meters at 2 meters per second squared. So if we go here and look at our equations of motion, we want an equation that can solve for v final that has acceleration and displacement and initial velocity. So if we look here at these equations, in my opinion, the easiest way to kind of see which equation we need is to kind of see in the problem how the problem doesn't mention anything about time. So it doesn't mention time. Meaning we're not asked to find for time, nor does it give us any kind of time interval of any sort. And so if we look at these 4 equations, the only one of these 4 that doesn't include time is this one. So if we look at this equation, it actually has all the pieces we kind of need, because we know what the initial velocity is at 0. We know what the acceleration is, that's 2. And we also know displacement is 150. And so we can actually use this equation to solve for our final velocity. So let's see, we have, write out that equation again. V final squared equals v initial squared plus 2 times the acceleration times displacement. Well, let's just ignore this because we know that's 0. And we want to find v final, but v final is squared, so we'll also have to take a square root. So v final is equal to the square root 2 times acceleration times the displacement. And now I'm going to put in all our variables at the end here, which is, this is kind of also a good habit to get into. I know a lot of people typically would have just plugged in the acceleration here and the displacement here and then went forward, but it's helpful and also useful to solve for your equation first in terms of the variables, and then just kind of plug in everything last. And so we have the square root now of 2 times 2 is 4. 4 times 150 is 600, I believe. So v final is going to be the square root of 600. And let me get my calculator. That's going to be about, and I'm rounding here. Let's see, where's my calculator? So I'm just going to say that's about 24. It's really 24.5, but I'm going to round down to 24.49, but let's just say 24 meters per second. Okay, so the first question was, if the runway is 150 meters long, can the plane reach the proper velocity to take off? if we know it must reach a velocity of 30 meters per second? Well, after going through our math here, we see that the final velocity once the plane reaches 150 meters, it's only going to be 24 meters per second. So the answer would be no, it's not enough. So this is not fast enough. So then, the next part of the question asks us, if not, which we know it's not, then what is the minimum length that the runway must have? So for the second part of the question, we slightly have to change our knowns and our unknowns. So for part two, part one, part two, our knowns are still, well, we still know the acceleration is the same. So 2 meters per second squared. The displacement we do not know because we're trying to find now what the minimum length has to be. But we do know that the initial velocity is still going to be 0. And we know the final velocity has to be at least 30. So the final velocity is equal to 30. And the unknown, in this case for part 2, is going to be, well, the unknown is actually the displacement, right? Because that's what we're trying to find. We're trying to find the minimum length that the runway has to be, or let's say the minimum displacement. So displacement S is a question mark. And so similar to how we kind of chose an equation for part 1, we'll go through the same process of saying, well, this is what we know, this is what we don't know. Let's see which one of these equations kind of best aligns with that. And again, since there's still no time involved, we can actually use this same equation used in part 1. Let's write this in red. So in part 1, we use this equation, V final squared equals V initial squared plus 2a times s. And so now we're trying to solve for s, this displacement. And we know that this is still 0. So now just kind of doing some quick algebra. All we have to do is divide over this 2a, and we see that the displacement is going to be equal to the final velocity squared divided by 2 times acceleration. And this is basically our answer now. So now we can just plug in our knowns. So we know that the final velocity has to be 30 and the acceleration was 2. So we have 2 times 2. So now this gives us, let's see, 900 over 4, which is, let's see, it's going to be 225 meters. So this is how long the runway, this runway has to be. The runway has to be at least 225 meters in order for the plane to reach a final velocity of 30 meters per second so that it can take off. So this is a kind of a classic example of what a kinematics problem would look like. It would give you, this word problem. From the word problem, find your knowns and unknowns, draw your picture, and then pick which one of your equations of motion would best help you out for the situation at hand. So let's see, I have another example here. This example says, in coming to a stop, a car leaves a skid mark 80 meters long. Assuming a deceleration of 7 meters per second squared, find the velocity of the car just before braking. Okay, so it's just slightly similar to the first example, I believe. But here, it says we have a deceleration of 7 meters per second squared. So again, once you see this part here, that should indicate in your mind, oh, well, the acceleration is constant, even though it's a deceleration. So we can actually say the acceleration is negative 7 meters per second squared because it's deaccelerating. So this basically should indicate that, well, we need our equations of motion for a constant acceleration, which are, again, these equations. And it says now we have to find the velocity of the car just before braking. So let's kind of draw a quick picture here. So car, and I guess at this point here, it starts to brake, leaving skid marks on the road, and the skid marks are 80 meters long. So we can say this is x naught, which is 0, and this is x final, which is 80. Okay, and so we know here it has some initial velocity. The car has some initial velocity going this way, which is actually what we're trying to find, because it says find the velocity just before braking. So that's the initial velocity. We don't know what that is. That's what we're trying to find. And in the problem, it says the car comes to a stop. And so naturally, we can assume that the final velocity then over here must be 0. Alright, so kind of just going through the process again, writing out our knowns and unknowns. We know the acceleration is -7, and again we know it's -7 because it says the car is deaccelerating, so that's why we have that negative there. We know the final velocity is 0, and we know the displacement is 80. And so the unknown would be the initial velocity. Start it this way. It's our unknown. So now that we kind of have our picture, we have our knowns and unknowns, now we would go and say, well, which equation of motion would, help us solve for the initial velocity the easiest. And so similar to this problem, how no time was mentioned, we can again use this third equation. And don't think that like we don't use these other equations. It just so happens that I chose 2 examples that need this same equation here. So we can use this equation again. Equation, I guess I'll call it 3. 1 plus 2, equation 3. So let's see, just writing out that equation, and we know that the final equals the initial squared plus 2 a times the displacement. Okay, so let's see, we're trying to solve for the initial velocity, and we know the final velocity here is 0. So this is 0, and the rest is kind of straightforward. We're trying to solve for v0, so subtracting that over, we see v0 is going to be equal to negative 2a times s square root. Again, where this negative here came from subtracting the 2as to the left hand side, and then taking the square root of all that. And then once we plug everything in, we see that this acceleration here, once we plug it in, the negatives will end up canceling out. So we have the square root of, now it's going to be positive 2 times 7 times 5, which works out perfectly because we shouldn't be getting any imaginary numbers here. And so that's going to be the square root of, let's see, 2 times 7, 14 times 5, 70. Oh, wait a minute, not 5. Where'd I get 5 from? It's supposed to be 80, right? Times 80. So 80 is the displacement. Where'd I get 5 from? I don't know. So 2 times 7 times 80. Yeah, times 80. And we get the square root of 1120. So the square root of that is roughly about 33 point, well, let's just say 33 meters per second. So the initial velocity must have been about 33 meters per second. So we can see, based off of just a skid mark here that was left on the ground, and also knowing the deceleration, which is -7, we were able to calculate how fast this car was initially going, when it started braking, which was 33 meters per second. All right, so the time is 10:08 now, so I'm gonna start speeding up a little bit, but hopefully you kind of get the idea and the process of how these kinematic equations kind of work. So I guess I'll do, let's see, do I want to do this example? I'm actually going to skip this example because it's going to take a bit of time. But if you want to do it later, I'll read it for you. It says a red car is speeding at 60 meters per second and passes a still police car, which the police immediately takes off in pursuit. Assuming the red car continues at a constant velocity and the police car is accelerating at 5 meters per second squared, find how, that's supposed to be how long it takes for the police car to catch up with the red car. So for this problem, we have basically two different objects that are moving at a constant acceleration. So you're going to have basically two sets of equations, one for the red car, one for the police car, and then from there you'll have to combine them a certain way to solve for how long it takes. So, but I'm not going to do that problem now because it's going to take a little time. What I would like to move on to is objects that fall downwards, or falling objects, I should say. And for objects that are, in free fall, they call it, or falling objects, uh, we can always assume that there's a constant downwards acceleration due to gravity of negative 9.8. So basically what we're saying is if we have, let's say this is the ground, you have an object here, it's falling, gravity, well, this object space is going to be accelerating downwards at a rate of negative 9.8 meters per second squared. And notice here that the acceleration is indeed negative because it's going downwards. And this is basically the case for any object that's in free fall. So let's do a quick example then, kind of illustrating that. So here in this example it says, if a stone is dropped from rest at the top of a tower, how long will it take for it to reach a downwards velocity of 30 meters per second? So these falling object problems aren't really too different. The only main difference is this acceleration here is given as 9.8. So let's see, let's draw a picture first. We have, I guess this is a tower. And I guess there's somebody up here, and they drop a stone. So this guy's holding that stone, and he drops it downwards. So looking at the problem, we know that the stone is dropped from rest. So we can say that the initial velocity up here is equal to 0. So we know the initial velocity is 0 meters per second. We also know it's not explicitly said in the problem, but we know since this object is falling downwards, we can say we know the acceleration is equal to negative 9.8 meters per second. And also some people call this g, just because this is the acceleration due to gravity. And so instead of a, some people like to call it g. These two things are interchangeable, or it might be a of g, to be more specific. So the acceleration due to gravity is negative 9.8. What else do we know? And it says how long, so we know we're trying to find the time. So time would be the unknown here, and we also know the final velocity is going to be 30. Okay. So here in this problem, it actually does have time involved because that's what we're trying to find. And let's see, we know the initial velocity, acceleration, and the final velocity. So if we go to our equations of motion up here, we know it's going to be either equation 1, 2, or 4, because those equations involve time. So if we look at equation 1, you see equation 1 is basically the equation for displacement. Now in our problem that I just mentioned, I didn't mention anything about the displacement or how far this stone is going to travel. So no, it's not going to be equation 1 or 4 because those are the equations for including displacement. And so if we look at equation 2, we notice that, well, this one Should work out perfectly for us. So writing that again, equation 2 says v final equals v initial plus a times t. Ooh, and I guess also too, I almost missed that this is actually, it asks for how long it takes for it to reach a downwards velocity of 30 meters per second. So just how like our acceleration is downwards, we know once this stone gets to, whatever point it's at, let's say here, the final velocity is also going to be downwards. So this should actually be negative 30. This should be negative 30. Similarly, the acceleration is going to be negative because it's also pointing downwards. And so now, let's go ahead and rewrite our equation here to solve for time, because we know the final velocity, we know the initial velocity, and we know the acceleration. So just rewriting this equation, solving for time, we see that time is going to be equal to v final minus v initial divided by a. Right. So now let's go ahead and plug in all of our values. So this ends up being the final velocity is negative 30. Initial velocity is 0 divided by negative 9.8. So we see here that, again, the negatives cancel out as they should, because time cannot be a negative quantity. And so we end up with this 30 divided by 9.8, which is roughly about 3. Let's see, divided by 9.8. Yeah, roughly about 3 seconds. So basically it takes 3 seconds for an object dropped from this tower to reach 30 meters per second. Now, I guess also too, before I move forward any further, I'll also mention that since now we're talking about falling objects, I'll ask you a kind of thought experiment that was done way back when Galileo was studying falling objects. Let's say we have a bowling ball or a big ball here, dropped from some height, and next to it we also drop this, I don't know, tiny golf ball, where this bowling ball is way more massive than this little golf ball, but they're both dropped from the same height here. So if we drop both of these, bowling ball and golf ball from the same height, which one would then hit the ground first? So, after talking about all this kinematics, you're probably going to say, well, since these are two falling objects, we can assume that acceleration is downwards, negative 9.8. And this acceleration due to gravity is basically accelerating both of these objects downwards with this acceleration. So then you would say, well, I guess I can just write an equation for motion to solve for how long it takes for each one of these balls to hit the ground. But as they found out when Galileo was studying this, that the mass of two solid objects, I'll say, they have to be for the most part solid. For two solid objects, if they're dropped at the same height, they'll basically both hit the ground at the same time. And that's because it has nothing to do with their mass, basically. which makes sense if we look at our equations of motion here. We see in each of these equations, there is no place for mass to be included. And so mass is almost irrelevant when it comes to equations of motion because there's no mass in here. And so all that to say is that the mass of an object doesn't necessarily matter when it comes to which one would hit the ground first. Of course, you can say, if one ball is higher, so let's say instead this ball is up here, then you can say, well, then which one would hit the ground first? Well, obviously, since this black one is closer to the ground, this black one would hit the ground before the red one if it started up here. But if they start at the same level, then they both hit the ground at the same time. Okay, so I guess with the last couple of minutes here that I have, I'm going to let's see. Let me see if I can quickly describe projectile motion, which is kind of a tedious topic to understand, but I'm gonna just kind of quickly go over it just so that you've seen it before you kind of get into class. So projectile motion is when now we get into kinematics in 2 dimension. And so beforehand, we were using our kinematic equations just in 1 dimension, either to the left and right or up and down. So for 2D motion, or 2D kinematics, now talking about projectile motion, we have some object, let's say a football, that's kicked or thrown, and it takes this arc-like path here. So now when we can also say, we have a football, we kick it at some angle with some initial velocity, and it's going to go through this path here. So this is also a constant acceleration problem because the only acceleration here is the downwards acceleration due to gravity. It's negative 0.8. Okay. So again, we can use our kinematics to kind of analyze this situation here, where we're going to have kinematic equations for the x direction and kinematic equations for the y direction, where these are basically the first 3 equations. I left out the fourth one, but these are the first 3 equations of the equations of motion, where these are specifically for the x direction and these are specifically for the y direction. And so again, we have to break it down this way because since we're now talking about 2 dimensions, this velocity vector now is going to have to be broken into its x and y components for us to truly analyze it, right? So we can kind of think, well, this initial velocity, kind of just speeding up here now, has a x component that's related to this angle. So we can see, well, v naught x, the x component, is going to be the magnitude of the velocity times the cosine, right? The cosine of the angle. And so now this is going to be the velocity you use here and here for your kinematic equations in the x direction. And similarly, I should write it this way. Similarly, we have this velocity, the y component, which would be v naught y. The y component is just going to be the magnitude of the velocity times sine theta. That's just the magnitude. And so now we kind of already see that first we have to analyze the angle with the magnitude of the velocity to get these x and y components of the velocity. that we'll be using in our kinematic equations. So they would be substituted here and here. And then, let's see, almost running out of time. So I guess the next thing I'll say is, if we kind of look at this path that a projectile motion that an object takes, we can kind of analyze it two ways. So we have here the horizontal and the vertical velocities. So let's say I go to this point here. Again, I can draw the horizontal velocity vector and the vertical and the horizontal. And so I drew it this way at this point because once this ball gets higher, the velocity in the up and down direction is going to be a little bit less. And then here at the peak, the ball basically kind of stops and starts to come back down. It's like if you stand in here and you throw a ball upwards, once it gets to its peak up here, it basically stops and then it comes back down. And so here we could say at the peak that the velocity in the y direction is 0, and then as the object falls down, the velocity is going to be downwards. So that's about it for today. Just gonna wrap it up here. Let's draw it this way. So the last thing I'll say is just kind of notice how on each one of these points on the projectile's path that the velocity in the x direction, which is this here, this blue arrow, is actually going to stay constant throughout the whole path, whereas the vertical velocity, this green arrow, is going to be changing. And so, it's upwards here, it decreases, at the top it's 0, and now it's going downwards, and now it's going downwards, even faster. And this is because the acceleration is only in the y direction, which is due to gravity. So I'm just going to leave it at that. Yeah, just leave it at that. Kind of recap a little bit what we talked about. So we talked about displacement, velocity, and acceleration. We talked about acceleration time graphs, velocity time graphs, position time graphs. How from these graphs, if we assume the acceleration is constant, how we get our equations of motion here. And then we kind of just played around with these equations of motion, applying them to a few examples. How we would kind of go about using them. First drawing our diagrams, writing out our knowns and our unknowns, and then from there choosing the proper equation of motion to help solve for the problem. And then lastly, I'll talk briefly about falling objects, where for falling objects, they're accelerating downwards due to gravity. And then I touched a little bit on projectile motion, which is any object that's going in this arc-like path in 2 dimensions, where the horizontal velocity remains constant because the acceleration is 0 in the x direction. I'll say that. And the vertical velocity is basically decreasing as we go up to the maximum height, and then increasing as the object falls back downwards. So hopefully I didn't go over that too fast, but it makes some kind of sense. And then, based off of all of these assumptions and everything I analyzed here, we basically apply that to the kinematic equations here, and they would end up getting much more simple. So with that, it is 10:30 now, so I'm just going to end it here. Uh, Please don't forget to do the survey, which I'm sure I think Elliot or Les will post into the chat. Um, and yeah, it's been fun. So, hopefully, uh, these camps will kind of prime you for your physics classes. I know we didn't get that deep or that far into them, but at least now, you've kind of seen these things at least a little bit before, they're introduced in class. Okay, so I'm just gonna stop sharing my screen.